All right, we are at 8.7. So we're skipping 8.6. 8.6 is pretty neat, but it's just not anything that I can test you on. 8.6 basically says there's a lot of computer programs that can do these integrals as well, especially helping us with approximations. 8.7, though, here we're going to be looking at something called numerical integration. I'm doing this in Word because it's a lot of words in this section, more than there is equations and stuff. But I'll kind of bounce back and forth a little bit. So, how does your calculator, how do these computer programs find these answers to integrals? So if you didn't know, your calculator can do integrals. Sorry, I had some stuff up here for my statistics stuff. Let me clear this out. So your calculator can solve integrals, but it can't exactly find the exact answer unless you have a super fancy calculator, but it can approximate the answer. So let's say we wanted to look at the graph x squared. So just graphing it. Oh, my window's all goofy. Sorry about that. Fix it as soon as it stops working. There we go. All right, so here we have the graph x squared. Let's say we want to find the integral of this graph. If you go to second and then calculate, you see this bottom number here, number 7. So this the integral f of x dx, and then just put the limits. Maybe we want to find the integral from 1 to 4. And then it just does the little area there, and it says, boom, the answer is 21. So this is the exact answer this time, but only because it's a whole number. If it ever is a fraction or something more complicated, of course, it'll only give you the decimal approximation. So let's talk about how things like your calculator and computer programs find that approximation for the integral. There's 2 different techniques that we're going to talk about here for numerical integration. Oh, you know what? There's one more thing that I want to say before we really jump into that. Some functions do not have a workable antiderivative. So I do want to point that out. There are integrals out there that are impossible to find the antiderivative for. Something like the integral of, I used to have a good one. I think x over sine x or something like that was one. So something like this, right? I think this does not have an antiderivative. It's been proven that you cannot find an antiderivative. I might be wrong about that one, but just know that there are some that exist out there. All right, let's jump into our first one. So the first one we're going to be looking at is called the trapezoidal approximation. And basically what this is going to be is it's an approximate. This approximates the region between the curve and the x-axis with trapezoids. I know that's not like super good definition, but it just is what it is. So the trapezoidal approximation approximates the region between the curve and the x-axis with trapezoids. So if we were in the classroom, I had all kind of pictures and stuff going. We were doing a lot of calculations here, but of course I don't have that luxury. So what I'm going to do is I'm just going to show you a picture of what this kind of means, and then I'm going to write out the formula for it. So we're going into the book to look at the picture here, and here we go. Let's say this blue line was the curve that we were trying to find the integral of. Remember, the integral is just the area under the curve. So instead of those Riemann rectangles that you probably remember from Calc 1, we're going to be doing these trapezoids. So using trapezoids to approximate the area under the curve. I hope you can notice that using trapezoids, we get a much clearer and much better approximation than we would if we were using rectangles. So that's what we're doing. Okay, now the formula. For the trapezoidal rule, which we're going to label as T, the area under the trapezoids is, so it's going to be delta x, nope, not that delta, the triangle delta, this delta. So delta x over 2, delta x represents the width of each of your trapezoids, okay? And then that's going to be times the first y value on the left-hand side of your first trapezoid plus 2 times the next y value plus 2 times the next one plus all the way down 2 to the n minus 1 plus just a single y sub n. Okay, so these y values represents the heights of the left and the right hand sides of your triangle. The reason that you only have a single y value for y naught and a single y value for y sub n is because those trapezoids are only counted once. So let me go back over the picture. For this first trapezoid, this height is only counted once, but this height is going to be counted twice because it's the right-hand side of the first trapezoid and the left-hand side of the second trapezoid. All right. Same thing for all of the heights that are in the middle. all the way until you get to the last height, y sub n is only counted once, again because it's on the right-hand side of that last trapezoid. Okay, so here's the formula. Let's look at an example. Let's try to look at the integral. We'll do the one that we kind of did before, but this is just the integral from 1 to 2 instead of 1 to 4 of dx. Okay. And then the question would say something like estimate using the trapezoidal rule with n equals 4. So it'll always give you that n value. Compare the estimate with exact value. All right, so estimate using the trapezoidal rule with n equals 4. That means to use this formula here. Now, first thing we need to do is we need to figure out what this delta x is. Again, that delta x represents the width of each of the trapezoids. You can also think of it like the partition width. If I am on the interval from 1 to 2, and I want to split up that interval into 4 different trapezoids, I'm going to be cutting that distance from 1 to 2 into 4 pieces, which means that my delta x is going to be 1/4. Right, it's 1/4 because I have a total distance of 1 from 1 to 2, cutting it into 4 sections. All right, other than that, we just need to find all those different y values. So let's go ahead and start plugging stuff in. So my total area using this trapezoidal rule is going to be that delta x 1/4, that divided by 2 times all of these different y values. So I'm going to write it all out in a little bit different way, just so I hope it's a little bit easier. So that first y value, y sub 0, is going to be starting at my left interval, my lower limit there of 1. Basically what we're going to be doing is we're going to be plugging 1 into my function. Plus 2 times plugging the next partition into the function. If I have a partition length of 1/4, that means I'm going to be plugging the next distance 5/4 into the function. That's just 1/4 plus the 1. Plus 2 times plugging the next one in, which is 6/4 or 3/2. Plus 2 times plugging the next one in, which is 7/4. Plus, this is now the last one, 2. So there's not a 2 out in front. All right, so I hope this is the same thing, right? I hope this makes sense to you. These are just the different y values. Plugging the first x value into the function gives me the first y value. Plugging the last x value into the function gives me the last one. And then those increments of 1/4 to get those ones in the middle there. The ones in the middle, remember, have the 2 coefficient out in front. At this point, just use your calculator. So 1/4 divided by 2 is 1/8. If I plug 1 into my function, and what I mean by the function is this x squared, I'm just going to get 1. Plus 2 times plugging 5/4 into that function gives me 25/16. Of course, the calculator will give you some decimal here. I wouldn't even bother doing what I'm doing here. I would just plug it onto the calculator. In fact, I have a calculator. Let's just do that. So what I would do is I would take that 1/8, and then I would multiply that by a bunch of stuff. So plugging 1 in, I get 1. Plus 2 times plugging 5/4 in is going to be 5/4 squared. Plus the next one, 2 times, that is 3/2 all squared. Plus the next one, 2 times, I think that's 7/4 all squared. Plus the last one's not going to have the 2 out in front, it's just going to be 2 squared. Great, so I get that. I'll change that into a fraction just to make it a little bit nicer. 75/32. Okay, so, all right, screw the fraction. We're going to leave it as a decimal. 2.34375. So we'll just do dot, dot, dot here because I don't feel like writing all that out. 2.34375, is that what I said? 34375. Yeah, great. Okay, good. So that's it. This represents the approximate area under the curve. Let's look at the actual answer. The actual answer for the integral of from 1 to 2 of x squared is that we would find the antiderivative there, which would be 1/3 x cubed, and then we would evaluate that from 1 to 2. If I plug 2 into there, I get 8/3, minus plugging 1 into there, I get 1/3, so final answer 7/3. 7/3 is the decimal, is 2.33333 forever and ever and ever. But notice how close our approximation is to the actual answer. We are 100ths of a decimal place off. Sometimes what the book wants you to do is to find the percentage of the error. To do that, you would just take the actual answer, subtract away your approximate answer, and then divide by the actual answer. So this comes out to be 0.446%. So that is our error, and that is how close our actual answer is. Okay, in the next video, we're going to do the remaining method, the better method.